The Raspberry Pi Zero W is an amazing computer at a very low price. Sometimes you can find them on sale for $5, and they range from that $5 up to $15. With this computer, you can use it like a desktop operating system, but you can also do lots of other interesting projects using them like an IoT device. In this workshop, I'm going to show you how you can turn a Raspberry Pi Zero W into a binary clock. Let's start with a simple question. What is this? The ones and zeros we call binary. Binary is the fundamental way that computers store and deal with information. They can be combined together to produce words. This is an example of two words. Can you tell what it is? In this case, it spells binary clock. And what about this? We recognize this as an analog clock, right? What is this? You got it. This is a digital clock. Can you guess what this is? This is what we're going to be building. This is an example of a binary clock. This is one that you can purchase. This is another binary clock. This is what the one that you'll be building looks like. Later on, I'll teach you how to read it. Just a couple more questions. What is this? This is a computer. This is an IBM mainframe computer, one of the largest computers available. And what is this? You probably recognize this as a laptop, which is another type of computer. And what about this? Of course, you recognize this as the very popular iPhone. But do you think about the fact that your smartphone is a computer? What do you think this is? And if you're following the pattern and think, well, it's a computer, you'd be right. This is actually the Raspberry Pi. This is the big sibling to the Raspberry Pi Zero W that we're going to be using in our project. We'll talk a little bit more later about the type of specs and technology in this device. This too is a computer. This is the Raspberry Pi Zero W that we'll be using in this workshop. It is a fully functional computer running the Raspbian operating system based on Linux. Last question, what is this? If you said Raspberry Pi, you were right. Now that you've been introduced to the Raspberry Pi Zero W, where the W stands for wireless, and the Raspberry Pi, let's take a little bit of a deeper look at both of these. So the Zero starts somewhere between $5 and $15 depending on where you purchase them, while the Pi 4 costs somewhere between $35 and $62 depending on how much memory you get. There's a difference in the number of cores between these two devices as well. For the Zero, there's a single core. For the Pi 4, there's 4 cores, and this will determine how much processing can be done on the device. There's a difference in clock speed for the CPUs as well. 1 gigahertz for the Zero, 1.5 gigahertz for the Pi 4. There's a difference in memory. So the RAM for a Zero is 512 megabytes, while the Pi 4, depending on which one you get, either comes with 1, 2, or 4 gigabytes of memory, which also correlates to the price difference. The USB ports, well, the Zero uses micro USB ports, where the Pi 4 uses full-size USB ports and has 2 2.0 USB ports and 2 3.0 USB ports that you can see slightly different in the black versus the blue colors of those ports. They both support Wi-Fi. While the Zero only supports version N, the Pi Zero supports both the 2.4 gigahertz as well as the 5 gigahertz and multiple bands as well, B, G, N, and AC. From a Bluetooth standpoint, the Zero supports 4.1, while the Pi 4 supports 5.0 and Bluetooth LE or low energy. For Pi Zero, you have GPIO ports, and you have the same 40-pin GPIO ports for Pi 4. From a hard drive standpoint, you can use micro SDs for both of the Zero and the Pi 4, which means either one of these devices could be used to complete this workshop. Both of these two computers have quite a bit of processing power, but they're still not as powerful as most cell phones today, and both of these devices have more power and capability than what NASA had when they put a person on the moon. Let's get more familiar with the Raspberry Pi Zero W. Along the top, you see the GPIO headers. GPIO stands for General Purpose Input-Output. It's what we'll be using later to control LEDs. Along the left-hand side is the micro SD slot. This is where you will insert the hard drive, a micro SD card. Along the bottom, starting at the left, is the micro HDMI port. We will not be using this in the workshop, but if you wanted to hook this Raspberry Pi Zero W up to a monitor, you could buy a mini HDMI cable or an adapter to a full-size HDMI cable, and you could hook it up to a monitor and use it just like a desktop. As I mentioned before, it's not running Windows, it's running the Raspbian operating system based on Linux, so it might look slightly different than your other computers. Then, to the right of that, there are two micro USB ports, and this is really important. The first one, the one on the left, is the data port. This is what you'll be using to transfer software programs that you write to the Pi Zero. Now, you can tell this one because right above it is a white label of USB. To the right of that is another micro USB port. This one is the power port. This is the one that you will plug into when you want it to run as a binary clock, just using power from the wall. And again, right above that is a white label that says PWR, or power. If you've gotten a kit from me, it will include these items. If not, you can go to bit.ly/binary clock workshop with a capital B, C, W to find a complete parts list and how to order each of the parts. The parts you need include a Raspberry Pi Zero W, or really any Raspberry Pi should do, a breadboard, 44 jumper wires. To make the project a little bit easier to follow, I like to use 21 short black jumper wires, 2 long black jumper wires. I like to use 3 sets of 7 colored jumper wires to make the project a little bit easier to follow. But again, color size doesn't really matter. You'll need a mini USB cable, a GPIO header. I like to use the solderless headers, a micro SD card, and 21 LEDs. I like to get 3 sets of 7 to make it a little bit more attractive. The agenda for the rest of the workshop is going to include some hardware setup, some Raspberry Pi Zero W configuration. Then we're going to do a lab called the Basic Hardware in GPIO, where we're going to light up an LED. Next, we're going to do a lab called SOS, where we're going to light an LED based on Morse code. Then we'll get to the meat of this workshop. We are going to do the binary clock lab. Then, to wrap everything up, we'll talk about some next steps. What else can you do with this Raspberry Pi Zero W? What other projects are there? And how can you continue your learning and fun? For the Raspberry Pi setup, we are going to install the female solderless headers. We are going to flash the Raspbian operating system to the micro SD drive, and we are going to enable SSH so we can remote into the Raspberry Pi. If you received a kit from me, I've already completed all of these steps for you, and then you'll just want to go through this so you can see what I've done for you. However, if you've acquired all these supplies yourself, this is a very important lab for you to go through, because the rest of the labs build on this. To install the female solderless header, it is easiest to use a jig, like this clear plastic jig. Place the Raspberry Pi Zero W over the screws on the jig, then lay the solderless header on top of the Raspberry Pi Zero, with all of the pins aligned with the holes. Next, we'll put the top of the plastic jig over top of the solderless header. Now, using a hammer, we will tap the top of the jig until the solderless header is flush with the board. There is another option. Instead of using the solderless header, we could get a regular header and solder it. So what we would need in that case is a soldering iron and some solder. And we would have to go to each individual pin, heating the pins up with the soldering iron, and then melting the solder onto those pins. So as you can see, using the solderless headers is a much easier process than going through the effort of soldering, and it prevents you from getting burnt. To finish this lab, you can download a version of the Raspbian operating system to your local computer. Then, using software like Etcher, you can copy that Raspbian operating system to your micro SD card. Now, in the detailed instructions I'll show you on the next page, what you can do is download a already configured one that has the SSH enabled, or there are instructions on how to enable SSH yourself. But I've tried to make it as easy as possible for you by making it a simple download. Here are the steps to the Raspberry Pi Setup Lab. Again, if I've given you a kit, all of this has already been completed for you. You don't have to do anything. If I haven't provided you a kit, you can always go to bit.ly/binary clock workshop, where you can find detailed instructions step by step walking you through each of these. Now stop the video, complete the lab, and when you're done, come back and we'll start on the next one. Now it's time for the Configure lab. During this lab, we will connect our laptop or computer to the Raspberry Pi Zero so that we can SSH to it or remote to it. Then we'll configure the time zone. Configuring the time zone is really important because, well, we're building a clock. Lastly is if you don't have a Wi-Fi, then you can manually configure the time. If you do have Wi-Fi and you configure the Wi-Fi, well, it's going to pick up the time automatically for you. And isn't that nice? Because who likes coming home to find out the power went out and the clocks are all blinking 12 o'clock? Well, with your binary clock, as long as it has Wi-Fi, you will have the current time. The first step is to take the micro SD card that you installed the Raspbian operating system on in the previous lab and insert it into the Raspberry Pi. Now, this card only goes in one way, so don't try to force it. It should fit in snugly, but insert relatively easily. Now we're going to connect our Raspberry Pi Zero W to our laptop using our micro USB cable. This will give us two things. One is it will provide power to the Raspberry Pi Zero. This is important to realize because if it gets disconnected and you reconnect it, it's like pulling the power out of the wall of a computer and plugging it back in. It's going to restart. Secondly, it's going to allow us to SSH or remote into it. So when we run commands, it will be as if we had a monitor attached to the Raspberry Pi Zero W. And again, like I mentioned before, this needs to go into the data port, which is the port more in the middle of the ports on that side of the board. To SSH into the Raspberry Pi Zero W will depend on the type of operating system you have. If you have a Mac, it's very easy. There's a program called Terminal built in, and when you get to a command line, you type SSH space PI at raspberrypi.local. And what happens is the Raspberry Pi Zero W creates a special Bonjour network that allows you to create a named device to connect to. And its name is raspberrypi.local. On that device, there is a user configured named Pi. So you're going to log in as that user. Now, when you are prompted for a password, the password is Raspberry, and that will get you in. On Windows, you'll have to install two things. If you don't have iTunes installed, you might have to install the Bonjour networking setup. The link is provided in the detailed step-by-step guide. You'll also want to install PuTTY. PuTTY is an SSH tool that will enable you to, from Windows, to SSH to the Raspberry Pi Zero. After you've installed it, you can open up the configuration, select Session in the left category, type in the host name, raspberrypi.local, that's the name that will be created based on the Bonjour network, and press the Open button. You'll get a command prompt, just like we talked about on the MAT terminal. It will ask you for the user, type in Pi, and then the password, which is Raspberry. Then you'll be inside the Raspberry Pi Zero. Once you're at the Raspberry Pi command prompt, you'll notice that it has a $sign. That's how you know when you're at the prompt. Type in the command sudo raspi-config, and it will give you a application with a menu. The first thing you're going to do is change the Wi-Fi so that you can get the current time. So select Network Options, then Wi-Fi, then you'll be prompted for your SSID, your network ID, and the associated password. Also, while we're in the Raspi config, we'll set the time zone. So select Localization Options, then change time zone. Assuming you're in the US, select US. And finally, assuming you're in the Eastern time zone, select Eastern time zone. If not, select your appropriate geographical area and time zone for where you live. With the Wi-Fi configured and the time zone configured, your binary clock will always be up to date with the current time. If for some reason you don't have access to Wi-Fi, you can always set the date manually. On the command line or at the dollar prompt, you can type sudo space date space -s space double quote the day of the month, 2 digits. So if it's the first day of the month, it'd be 01, space 3-letter code of the month, space the 4-digit year, space the hours with 2 digits, colon, the minutes, 2 digits, colon, the seconds with 2 digits, double quote. Please note though, that anytime you unplug and plug the binary clock back in, you'll have to reset the date and time because it will lose it every time it loses power. Now, using the detailed instructions at bit.ly/binary clock workshop, please complete the configuration lab. Connect the Raspberry Pi using the USB cable and configure SSH. Next, configure the time zone and the Wi-Fi, and if you don't have Wi-Fi, manually configure the time. Now, stop the video, complete the lab, and when you're done, come back and we'll start on the next one. In the basic hardware and GPIO lab is where the fun begins. We are going to learn how to wire up an LED to the Raspberry Pi Zero. Then we're going to learn how to programmatically control it using Python in the standard Python way. And then we're going to learn how to use a different library called the GPIO 0 library to make that code even easier to read. This is how we're going to wire up our LED so we can turn it on and off. On, off, on, off. So what is an LED? LED stands for light emitting diode. And just like you saw from the animation, a light emitting diode is basically a light bulb. So this wiring might look confusing at first, but it's not really. What we're going to do is build a circuit, much like you might have learned in school, going from a battery to a light using a positive, and then from the light back to the battery using a negative. And we're going to do the same thing here. So we are going to plug one end. If you have a green wire, we're going to plug one end of the green wire into GPIO port 21. I'll talk more about the ports in a moment. And the other end into J29. That's going to be your positive wire. Then that's going to travel through the breadboard, which I'll explain more later, to the LED. Now there's an important thing about the LED. The LED has a long leg and a short leg. The long leg is the positive side. So you're going to plug the long leg of the LED into F29 and the short end into F30. Now, just like with a circuit, you're going to have to go negative. So you're going to take a black wire, which usually represents the negative, and in this case, the short black wire is best, from J30 to the blue line in the breadboard. Electricity is going to travel down that blue line till it gets to a long black wire, and that's going to plug into the first row. Then the other end of the black wire is going to plug into the ground, which is where the negative terminates. Let's take a moment to look at the GPIO ports. Again, that stands for General Purpose Input Output. And not all of these ports are created equal. As you can see, some of these ports are intended for power. Others are intended for ground, where the negative returns. The ones identified with GPIO are used for the general input-output, and then there are some other special ones for different types of protocols. Ports can be identified by either their PIN number or their GPIO number. To use this diagram, you'll have to align the diagram to the Raspberry Pi Zero. We do this by using the top left port, which is a square on both the diagram and the board. And an astute observer will notice we have a challenge because we have a solderless header installed that is covering up the ports on the board, so we can't see which one is square. So the way I like to remember is to use the micro SD card slot since it is square and right next to the square port. The other thing in this lab I want to talk about for a moment is the breadboard. Now the breadboard is used instead of soldering because it's easier to experiment with, to prototype, to try things out. And again, you don't have to worry about burning yourself on a hot soldering iron. At first, the breadboard might seem a little intimidating. I know it did for me. But I'm going to explain it, and you'll see that really all the breadboard is an extension of wires. Notice the red rows, or the ones with the positive signs above them, are both on the left-hand side, and they represent a long wire going down from the top to the bottom. Similarly, the negative side, where the blue line represents a long wire running from the top to the bottom. Then, from A to E, in each row, also represents a short wire, while F to J, on the other side, also represents a separate short wire. So by plugging two jumper wires into A1 and E1, we are just extending that wire. During this lab, you'll use a general purpose programming language called Python. It's very popular. It's used for things like IoT devices, like we're doing now, data analytics, big data, and machine learning. At the command prompt, you will want to type Python 3, all lowercase, to start the Python interpreter. Please note, Python is a case-sensitive language, so make sure you use the proper upper and lower case. The import GPIO as GPIO makes the standard Raspberry Pi's GPIO library available to your code as the GPIO alias. The GPIO set mode says whether we are going to use the pin numbers or the GPIO numbers in our code. BCM says to use the GPIO numbers. You can use the uppercase board if you want to use the pin numbers. You can then use a GPIO setup to tell it whether you want to send power to a GPIO port, like in this case GPIO port 21, as opposed to reading power from a GPIO port, like you might do from a sensor. So as a reminder, when we reference 21 in our code, we're referencing that GPIO port, or that bottom right port on our board, which is where we have the LED plugged in. The next line, GPIO output 21 GPIO.high, says that we are sending or outputting electricity to port 21 at its highest level, which will in turn light up the LED. The next line, GPIO.output 21 GPIO.low, says that we are going to output the lowest amount of electricity to the LED, which in turn turns the LED off. The final line, exit parentheses, says to leave the Python 3 interpreter. Now that we've looked at the standard way of doing the Raspberry Pi Zero GPIO development in Python, you may have noticed it's not a very intuitive way of actually doing the GPIO interaction. For example, high and low, that's not usually how we think about lights. We usually think about on and off, and having to repeat port 21 3 times, and having to actually say, let's set up the output. So what we want to do next is look at another library that can help simplify using the GPIO on Raspberry Pi Zeros. The simpler library we'll use is called GPIO 0. And just like with the standard library, from the command line or the dollar prompt, you will type Python 3 to enter the Python interpreter. Next, you'll type in the line from GPIO 0, import LED, where LED is the alias that you'll use to reference that library. Next, you'll create a variable based on the LED alias, where you'll pass in the port number, just like we do with the standard library, to identify where we'll be sending the signal. Now we'll turn the LED on by saying LED.on. Doesn't that make more sense than high? To turn it off, it's simply LED.off. One of the things you'll be asked to do during this lab is to create a looping statement. The particular looping statement you'll use is the while statement. And anytime you use a statement like this or a conditional statement like an if statement in the language of Python, you have to indent. That's how they do a block of code in Python. That's how they group a block of code together, is the indentation. So that can be a little confusing if you've not done that before. So to indent, you use the tab key. So if you look at this code here, you see ... and then a bid space. Well, that's because a tab key was used. And that means anything after the while true colon that's indented will be a part of the same block. Then to get it to execute that block, you have to press enter twice. So you'll see ... press enter again, and that will end that block of code. So this particular statement here will say while true, which means it will go on forever. Then it's going to turn the light on by passing it a high. It's going to sleep for 1 second, and then it's going to turn the light off with a low and then sleep for another second. And now it's time for the basic hardware GPIO lab. You'll wire up the LED like we talked about. Then you'll control it programmatically using the standard Raspberry Pi library. And then finally, you'll do it again using the GPIO library. Now, stop the video, complete the lab, and when you're done, come back and we'll start on the next one. Now that we completed the basic hardware lab, next time you see a glowing Apple logo on the back of a laptop, a power light on a laptop, or a backlit keyboard, you'll know how they did it. In the SOS lab, you'll be combining what you already learned in the previous labs, looping, Python, lighting LEDs, to do a new pattern. You're going to do Morse code to present SOS, which is used in scenarios where you're in trouble and you need help. And that pattern is short light, short light, short light, long light, long light, long light, short light, short light, short light. And then you'll repeat that over and over again until you're rescued. So the good news is, if you have your binary clock and you're stranded on a deserted island, you'll be able to signal that you need help. Now, stop the video, complete the lab, and when you're done, come back and we'll start on the next one. Now it's time to build the binary clock. But before we build it, let's make sure we have a common understanding. So we're going to review some binary and how to read a binary clock before we start building it. So what is binary? Well, in mathematics and digital electronics, binary is a number expressed in a base 2 numeric or binary numeral system, which uses only two symbols, typically 0 and 1. We often will say on or off, true or false, high or low. And this is basically the fundamental building blocks of a computer. All a computer can do is determine 1 and 0, on or off, and it builds those in combinations to help it think and process information. Let's compare the binary number system to one you're already familiar with, the decimal system, the one you probably learned in kindergarten, counting to 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now let's look at what that would look like in binary. In binary, a 0 is simply a 0. For the rest of the numbers, depending on the position, which column that they're in, the 1 and 0 have different amounts, starting with the first column being 1, the second column being a value of 2, the third column being a value of 4, and the fifth column being a value of 8. Now let's look at a couple numbers to see how this works. Let's start with 1. Just a 1 is in the ones column, and that is the value of 1. A 2 in decimal is represented as a 1, 0. So that's worth 2. And there is a 0 in the 1 column, so the total is 2. 2 plus 0. In binary, the 3 is represented with a 1, 1. So there is 1 in the 1 place and 1 in the 2 place. So 2 plus 1 equals 3. A 4 in binary is represented with a 1, 0, 0. So there's a 0 in the 1's place, a 0 in the 2's place, and a 1 in the 4 place. So 4 plus 0 plus 0 is still 4. And the last one we'll do is 5. 5 is represented as a 1, 0, 1, or a 1 in the 1's place, a 0 in the 2 place, and a 1 in the 4 place. So 4 plus 0 plus 1 equals 5. So now hopefully you can appreciate this hysterical joke. There are 10 types of people in this world. Those who understand binary and those who don't. And now you understand binary. Now let's look at counting binary in a binary clock. There are 3 columns. There is the hours columns made up of the tens column and the ones column. There's the minutes columns made up of the tens and the ones. And then there's the seconds made up of the tens and the ones. There are also 4 rows. The first row represents the value of 1, like we just talked about with binary. The second column represents the value of 2, the third, 4, and the fourth, 8. So here's one for illustration. In the hours, in the tens column, the number 1 is lit up and nothing in the ones column. So that's 10 o'clock. In the minutes, in the tens column, the 1 and the 2 are lit up. So 1 plus 2 is 3. In the ones column, you have 1, 2, and 4 lit up. 1 plus 2 plus 4 is 7. So it's 37. In the seconds column, the fourth one is lit up in the tens, so that's 4. And then the 8 and the 1 are lit up, so 8 plus 1 equals 9, or 49. Here's one for you to guess. Why don't you pause the video and figure out the number, then start the video and I'll give you the answer. If your guess was 84611, you're right. Usually binary clocks are horizontal like we just covered. However, because of the size of the breadboard we're using, we're not able to do that. So we're going to rotate our breadboard 90 degrees to make it vertical. So likewise, we're going to take that horizontal binary clock and we're going to rotate it to be vertical as well. So it's going to go from this to this. Let's try a couple more tests just to make sure we understand how to read it now that it's vertical. So what time is this? Pause the video to figure out and start the video again and I'll tell you the answer. If you guessed 12:09:57, you're right. Let's do one more. Pause the video, figure out what time it is, and start the video again for the answer. Hopefully you guessed 9:30, because if you did, you're right. Maybe what you learned from this exercise is that the problem with the binary clock is by the time you figure out what time it is, you're probably already late. So now it's time for the binary clock lab. During this lab, you'll be wiring up 21 LEDs. You'll be executing a Python script that already has the code written to set the time and make the LEDs light up. If you wish, you can go ahead and try to write this script by yourself as well as a challenge. And then finally, if you want, you can run the auto configuration so that as soon as the binary clock is plugged into the wall, it starts displaying the time. Now let me give you a couple suggestions or hints before you get started. This is a picture of half of the binary clock. This is the ones column. And it may look a little daunting at first, but there is a pattern to it that you'll catch on to very quickly. If you look, every other one is a black wire, and every other one is a colored wire, starting with green for the seconds, and then yellow for the minutes, and red for the hour. And for the ones column, everything plugs into the right side of the Raspberry Pi Zero. And this is a tens column. Everything follows that same pattern, except for this time it will plug into the left-hand side of the Raspberry Pi Zero. And then finally, one other bid suggestion is to start the clock Python script right away. So as you are actually wiring it up, you will start to see some of the LEDs light up. And the seconds in particular are a lot of fun because they will be changing constantly. So pause the video, complete the step-by-step instructions as a part of the lab, then come back for some very important final thoughts. If you're interested in doing this project again, this is a parts list and prices paid when buying these components in bulk. The overall price for one of these kits is somewhere around $21. If you do use the solderless headers, it's not a requirement, but I do highly recommend the jig, as it does make installing the headers significantly easier. And if you don't want to find all the parts yourself, there are plenty of kits out there for both the Raspberry Pi Zero W and the Raspberry Pi in many different price points, ranging from $26.99 to $89.99 and above if you want things like keyboards, mice, and other things. If you do want to keep your binary clock as a binary clock and plug it in the wall so it always has the current time, you can either buy a micro USB power supply, or you can find an adapter, maybe from an old cell phone laying around, for your USB cable that's included in the kit. Now have some fun. Go challenge your family and friends to see if they can tell what time it is. Now I hope you've had some fun and you've learned something along the way. But one of my other hopes is that you feel comfortable taking this apart and maybe building something else new out of it once you're done playing with the binary clock. One of the important lessons that I learned early with computers is how to take something apart and put it back together. But unfortunately, with today's modern devices, laptops, cell phones, they're very difficult to take apart and put back together. So please, keep this as your own computer, as something that you should feel comfortable with messing around with. You really can't break much. It's only a $10 computer, so even if you do break it, well, they're pretty easy to get new ones. If you need some ideas of what to do with your Raspberry Pi, well, you can Google Raspberry Pi projects, or go to any of these links for suggestions as well. But have fun using this Raspberry Pi in new and fun ways. If you have any questions or run into any problems along the way, feel free to email me at javajud@gmail.com. I hope you had fun, and I hope you learned a lot.